So we're looking at these exercises from the 2-unit Fitzpatrick book, 14A, 13579, and our context is that we sort of learned what limits were, and we know how to get some basic limits. And then we also have an idea of limit laws, which allow us to get more complicated limits if we can show that they're expressible using basic limits, using addition, multiplication, subtraction, and division. Okay, so we're gonna use, so when we have that context, it's going to be natural for us to sort of try and use that rather than going from the definition. Though sometimes it might be important to be aware of the definition. Okay, so like for the first one, for example, we could really, if we got this question on its own, we could really see what happens to this expression as x approaches 3. Okay, but since we have an idea that we have two basic limits here, we have a constant. Okay, we know that doesn't change when x does something, so this is going to be equal to 3. And we know that another basic limit is if it's just x, okay, and x approaches 3, then the limit will also be equal to 3. Okay, so we did these separately, and we're assuming that we know that the answer, this is 3 and this is 3, okay? And since they exist, okay, then the limit of this product is the same as the product of its limits. Okay, so that's one of the limit laws. And then since these are both equal to 3, the final answer is 3 times 3 is 9. Okay. So something similar can be done here. Okay. So we know this is the same as the limit x goes to 3 of 9 minus the limit as x goes to 3 of x, okay, squared. And squaring is the same as just multiplication by itself. So we're just using this thing here again. So all of these limits exist, right? We said this is 3, this is 9, and this is just a combination of these. So the limit of this combination is a combination of these limits since they exist. Okay, and we'll see that. So this will be 3 squared, this will be 9, 9 minus 9 is 0. Okay, you kind of got the hang of this. You might want to try the next one yourself. You have limit of x goes to 4 x all squared times the limit as x goes to 4 x plus the limit x goes to 4 of 2. Okay. And so that's going to be just the same as putting x equals 4 in here. Okay. So you got 4 is 16, 4 plus 2, 6. So 16 times 6, 96. Okay. Okay, so you could probably extrapolate 7 yourself, and basically anytime we see it does, these are sort of polynomials in the variable. Anytime you have that, you can just substitute whatever the number is that the variable is approaching. Okay, and another way of saying that is, as we'll eventually learn, is that polynomials are continuous, or polynomial functions are continuous. So anytime you want to take a limit, it's the same as evaluating at wherever the limit is going to. Okay. Now 9 is interesting because that's sort of a different theme. It's a different kind of thing. So now we have division. Okay. And the thing that's interesting about division, or the thing that's watch out for in division, is that you can't divide by 0. Okay. So if we wanted to just do the same thing we did before, well, the problem we'll have is x goes to minus 3, but when x goes to minus 3, x plus 3 is 0. Okay, so we'll have to, if we do the same thing, we'll divide by 0, and we're not allowed to divide by 0. Okay, so now this is where it's helpful to know the definitional limit, because in the definitional limit, sort of to get close to the final expression, sufficiently close, you're allowed to get, like as close as you want to the final expression, you're allowed to get sort of close enough or sufficiently close to minus 3. But there's nothing that says you have to actually equal minus 3, okay? So you're allowed to sort of just get close to minus 3, close enough for this expression to be close to the thing that you want it to be, but it doesn't have to actually equal minus 3, okay? So if it's so if we think about all the other x's that are not minus 3, okay, then these two things can just cancel, okay? And so what happens is the expression, when we yeah, I mean the expression is not allowed to have x equals minus 3 anyway. So if we know x cannot be equal to minus 3, then this expression simplifies to x plus 5, okay? And then with the understanding now that x is not equal to minus 3. I guess I only wrote that because here it's explicitly not equal to minus 3. Here it's more implicit if we're saying it's the same expression. You don't actually have to write this, okay? I think in high school it's, you don't, well, I just wrote this for my own notes. But there is sort of a difference between those expressions. But anyway, but now you have the same situation you were in before, and you can just take x equals minus 3 here. And the trick is you're not really saying x equals minus 3. You're saying this limit is the same as if you had put x equals minus 3. It's just that, so the limit would be, this minus 3 is 2, right? So we're saying we can get as close as we want to 2, okay? We can get as close as we want to 2 as long as x is close enough to minus 3. Okay, that's what it means for this limit to equal 2. It's not that now we can make x equal to minus 3 where we couldn't before. It's that now this limit, yeah, and it kind of makes sense with this there as well, right? Because we can get close enough to minus 3 while not being minus 3, okay? So the fact that this answer is 2 means that we can get as close, we can get this expression here can get as close as we want to 2, okay? Provided we're close enough to minus 3. So if we want to get within the 100 million of 2, we would try to get sort of within 100 million of minus 3. Okay, and that would work because the 5 doesn't do anything. Yeah, so we're not, so yeah, I mean, this point is probably not labored on, like this point is probably just skipped over most of the time, but, and you probably won't even be, you probably won't be tested on this anymore, but I think it's important to get things right in your head. Otherwise, if you're just storing contradictions, you're kind of missing the point of this, the educational purpose of learning this, because you're probably not going to use this. You're going to use your brain, and that's what you're developing.